Today we will discuss about the light sources and detectors that are being used in the fluorescence spectroscopy as well as photochemical experimentation. There are a variety of light sources available commercially, and we have to identify the right sources for your instrumentation and use it for the appropriate and very good performance. If you look at the commercial light sources, one of the well-known light sources, incandescent light sources, which is Thomas Alva Edison lamp, which you can call it like a tungsten lamp also. And I given the light sources pictures as two columns. First column is referring to the one written in the red. Second column is the one written in the black. First one is an incandescent lamp. The second one is a halogen lamp. Halogen lamps are the general lamps used in the UV visible spectroscopy instrumentation for the visible region. And we have the semiconductor light sources. They are nothing but the LEDs, light emitting diodes. They have a wide coverage of visible and white light and UV also. The other one is the fluorescent light. Fluorescent lights have different formats: tube lights, compact fluorescent lights, CFLs. Now presently we are moving towards the LED technology, white light LED technology for the domestic and all the applications, street light application and so on. Earlier the street lights, they were also using a sodium vapor lamp. Sodium vapor lamp gives you yellow light, which is a two wavelength light. Two wavelength lines, you get it. The other one is a mercury vapor lamp. They come in a different formats and different models. We use it in the laboratory for many applications. Next is on the metal halide lamp. Metal halide lamps are being used many applications like a car headlamps, projector lamps, and so on. They are much brighter. And you have the gas discharge lamp. They are nothing but the inert gases. They discharge light, helium, neon, xenon, and so on. These are the basic family of light sources available commercially. If you see the instrumentation application, we'll be using halogen lamps, LEDs, mercury lamps, and so on. Now let us focus ourselves on the mercury light sources. When you look at the mercury light sources, they have the low pressure mercury lamp, which is also called as a pen rail lamp or a pencil lamp, which selectively gives 254 nanometer, and it also gives a visible light, which are very low intense compared to the 254 nanometer. If you want to filter the UV light out of that, you can put a UV filter jacket on this, you will get a visible light, so which gives 365 and other visible lines. Out of the visible, 365 is intense, others are weaker ones. But overall, this is a low intensity mercury lamp which can be used for the calibration purpose for the spectrometers and so on. Next lamp is a medium pressure lamp, medium pressure mercury lamp, which can be used for the instrumentation and the UV visible light source. And this has a filament, and then you have the lamp filled with the mercury gas. Sometimes you can also have the argon filled along with this. And these medium pressure mercury lamps are really useful for the UV and visible lines. And the medium pressure lamps have the pressure of gas atmospheric pressure, whereas low pressure ones have the lower than the atmospheric pressure. And if you want to see that the broadening of the spectral lines that is happening, you have to increase the gas pressure inside. So as you keep increasing the gas pressure inside, the spectral lines, narrow lines get broadened, and you get a broad spectral region emission of the light from the light source. Now you have a high pressure light sources which can be more than the atmospheric pressure. Something like a 10 atmospheres of gas is filled inside the lamp, so you need to have a very high thick wall glass lamps. And whenever you use high pressure lamp, there is always a possibility of explosion, and you have to be cautious about the usage of high pressure lamps. And that is the reason why the wall thickness of the glass bulbs will be very high, so that it withstands the high pressure of the gases that are filled inside. Now these are low pressure, medium pressure and high pressure are the general lamps used for the laboratory applications. We also have the other two class of lamps. They are called as the water cooled lamps and the super high pressure lamps. So they don't find any application in the laboratory, but still for the sake of completion of the entire mercury lamps, so I given you the information on the water cooled and super high pressure mercury lamps. So these are the family of mercury lamps, and out of this low pressure, medium pressure, high pressure, you will find application in the photophysical and photochemical experimentation. Now, if you compare the spectral output of these two lamps, low pressure and medium pressure, you can see that the low pressure has the narrow line, which is a single line, almost single line with a 254 nanometer. You also have the very weak other weak lines at 365 and other visible region. If you look at the medium pressure, they are more intense. In fact, these signals are multiplied 10 times, and that means the line intensities are amplified and given you for the sake of comparison. But otherwise, the mercury lamps give you more intensity when compared to the low pressure lamp. So as you increase the pressure of the gas inside, not only it broadens the spectral region, it also increases the intensity of the light emission. That is most important thing. And you can really select these lamps depending upon your requirement. If you want to really go for a 365 or more on the visible region, good to select a medium pressure lamp. And if you want to have only two UV region, you can select your low pressure mercury lamps. Nowadays you also have the LED light sources. The LED light sources can also be used in place of mercury lamps. They are available in the UV formats, UV region as well as the visible region. They also have the white LEDs, which is covering the entire visible region. And choice of the lamp is yours. So based on the requirement, you can have a different wavelengths like 365, 385, 395 or 405. So these lines are very, as you know, you will have a spectral width around plus or minus 5 nanometer around this. They're all monochromatic, and UV lines are available, and you can have a choice of the UV LEDs also. Now when you look at the spectral distribution of all these LED light sources, they cover the visible, as I already mentioned. You can also have the LED at 365, it is called as the UVA region. And if you compare the LEDs and mercury, you can see that the mercury can give you UVB and UVC, whereas LEDs are limiting themselves at the region of UVA. So if you want to really go into the UVB and UVC region, you have to have a choice of the mercury light sources. If you have the high pressure, medium pressure mercury, you can have visible lines also. And this doublet line that you are seeing around 540 is very important for the spectral resolution calibration. And you can see that the lines are coming up at different positions of the visible also. Now you can see all this spectral distribution of mercury lamps and the LEDs. There are a variety of light sources, but LEDs you have to have every wavelength one LED. That is the one disadvantage. Whereas if you have a medium pressure mercury, it can cover the entire region of the ultraviolet and the visible. So this is how you can have a choice. Either you want to go for a LED or a mercury source. So this is the set of lamps available. And when we talk about UV, you have to understand the UV classification. So UV has the A, B, C classification. If you look at the natural light source, sun as the light source, and UVA reaches the earth, UVB also reaches but less when compared to the UVA. UVC is completely curtailed by the ozone layer. Now the regions of UVA is somewhere 320 to 3400, UVB is 290 to 320, and UVC is 100 to 290 nanometer. This is how you can see the UV regions are being classified. And this is the basic understanding. Everyone has to understand what kind of a UV region you are talking about it for different applications. So UV classification one has to realize. Now you should also understand the spectral distribution, as we already mentioned the number. You're looking at the spectral distribution and the influences of all this UV radiation. UVA, as we already said, is almost closer to the visible region. UVB is little more in the deeper. UVC is the deep UV region, and UVC is basically can be used for disinfection. It is basically, it's called 264 is called as a peak germicidal efficiency wavelength. So it is mostly applied for the disinfect applications. 264 nanometer is the wavelength that is responsible for disinfection applications. So you should understand the influences of UV region A, B, C on our system also, and the wavelength of UV A, B, C, and so on. Now you should also understand UVC can even kill the superbugs, that is really resistance to the antibiotics, and good to have the exposure to UVC if you want to kill the superbugs. Now the next class of the lamps that you have is the xenon lamps. Xenon lamps are generally used in spectrophlorimeters. It can also be used for the photochemical experiments, and xenon lamps are very intense when compared to the mercury lamps. So we always say that the xenon lamps are almost like a sun in your laboratory. It looks as bright as your sun as you see with your bare eyes. So you have to be cautious. You should not expose your bare eyes to the xenon lamps. They will kill your eyesight. So they will damage otherwise. So it is important. You must have the proper protective glasses when you see any intense lights. Even if you look at the sunlight for some time, you will see that you may feel like becoming blind. So it will take some time for you to look at the things normally, because intensity is quite high. So anything that is more intense you should not see with your bare eye. This is the first principle, you should realize it. And these xenon lamps are coming as an arc lamp. They are basically arc lamps at the different wattages. You can have it in the region of 100 watt to 1000 watt, and you can also have it in the form of a pulsing arc lamps. This is also possible. Additional pulse voltage can also be given. So these are the advantages of the xenon lamp over the mercury lamps. Such kind of a pulsing is not possible with your general mercury lamps. You can use it like a CW lamp. Xenon lamp has an advantage of usage like a CW lamp as well as a pulsing lamp. Now, if you look at the spectral output of the xenon lamps, it covers the entire UV region to visible and IR region also. And you can see the general format. They are in the format like a bulb, arc lamp, bulb sources, or you can have it like a ceramic sources. You have a reflector inside, so it will be more intense and more focused towards the application. So it is easy to focus your ceramic focusing type of lamps, whereas you have to put a lot of optics in front of the bulb type, and you have to put an outside external reflector, whereas here you don't need any such reflectors to focus the beam. So these are the advantages of xenon lamps. They are very intense. Can have it in a different formats. So you can, as I told you, you can have the xenon lamps in the flash lamp formats also. The flash lamps can be in a different sizes, different powers, and that makes these flash lamps applicable for many of the applications for flash excitation, optical pumping of lasers, and so on. So if you want to do a flash photolysis with a flash lamp, you can use these flash lamps, or if you want to use the laser pumping, you can use the flash lamps. They have a different kind of a pulse width of the flashes. You can have it from microseconds to milliseconds. So these are the advantages of xenon. Xenon, you should keep in mind, they are very intense light sources, which finds a lot of application in the photophysical and photochemistry instrumentation. In particular, fluorimeters generally have the xenon lamps. If you want to measure the phosphorescence lifetime in spectropolarimeter, they also have an additional flashing xenon lamps with a millisecond pulse width. So this is how xenon lamps find a lot of application in the instrumentation. Whenever we talk about light source, you must be able to measure the intensity of light source. There are a number of physical devices available to measure the intensity of light sources. You can see that the measurement of UV intensities is possible with the UV radiometers. They have radiometers which can be used to measure the intensity of the UV light. You have LUXMETER, which can be used for any intensity, whether it's a UV or a visible light. It can be used for any domestic application also, find out how much is the intensity of the light that is coming out of your lights that you are being used at home. Many light applications, it is possible to measure the intensity using a LUXMETER. Now you can use a power meter if you are measuring the intensity of a very intense light source like a lasers. We'll be learning more about this power meter when we study about the lasers. They have the detector, otherwise you call them as a sensor. This sensor is called the thermophile sensor, thermophile detector. Here it absorbs the photon, converts into heat, and the increase in temperature is measured to measure the power of the light output. So this is basically a volume absorber type of the thermophile detectors. So it is being used to measure the intensity of the laser. So this is basically called as a power meter. These are the three variety of the light intensity measuring devices which can be used in the photophysical and photochemical instrumentation. Now, when you talk about intensity of light, you should also understand the units that are being used in the intensity of light measurements. So, candela is the general unit. Candela derives from the candle. One candle light intensity is called as a candela. And this is the unit used in the representation of the lighthouse intensities. You know, when you see the lighthouses at the harbors or the sea ports, you always see that the lighthouse intensities are being represented as how many candelas that they use it. And the other unit is a lumens, how many lumens. You know, lumens is a common measurement. You always use it in your LCD projectors or home theater projectors. So you call them how many lumens, 1000 lumens or 3000 lumens, 3500 lumens, and so on. So this is nothing but the brightness of the light source that you are using it. The units they are using is a lumens. Other units they use it is a power and energy unit. When it is a continuous light source, they always use a unit called as a power, which is in the form of watt, milliwatt, microwatt, nanowatt, and so on. And if you are using a pulsed light sources, the energy unit, the intensity units are nothing but energy. You always represent them in the form of a joule, millijoule, microjoule, nanojoule, and so on. You know, as you see the joule, the intensity is more. As the units go down, and millijoule, microjoule, and nanojoule, the intensity is lower. So you can see that the four basic intensity units are used to represent the intensity of the light sources: candela, lumens, power, and energy. Now, when you handle UV lights, so you already see that the UV lights are hazardous. So you should understand the hazards and also the safety procedure that you should follow it when you handle the UV light. UVA radiation, 315 to 400 nanometer, it's a near UV light, or otherwise you call them as a black light, is photobiologically active, but it can really produce, when you expose to this light, it can produce tanning and some burning of the skin. Sometimes, you know, it leads to cataract also. When you are overexposing this light to your eye, it leads to cataract. So you must avoid the exposure of this light to directly to the eye. The next is UVB radiation. It's called the middle UV, and it can have really UV generally causes skin tanning. sun burning, and cataract. So this is most important thing. UVB is also very harmful, so you have to protect your eyes and skin. UVC is most dangerous. We already said it's a germicidal UV or far UV, and you should not expose any of your body and eye to this UVC radiation. And A and B can be, but you have to protect in all these aspects. So protecting your eye and skin is very important. It is the most important safety procedure. You should follow it. You can protect your entire face with a face mask or the gloves or with your goggles for your selective protection of eye alone. So these are all important when you expose to the ultraviolet radiation. So you must take all the precautions to protect your body from the unwanted exposure, unwanted damage that can happen to the body organs. So there is also threshold limit. They always use it. So you call it it is a wavelength dependent limits. So when you look at the 240 to 300, what is the limit that you can have is, and 10 millijoule per square centimeter with a minimum TLV, and TLV threshold limit is something like a 3 millijoule is the minimum, 270 nanometer is the most dangerous UV radiation, 240 to 300. Now, if you are least hazardous wavelength, longer wavelength, you can have up to 1000 millijoule per square centimeter. So that is the TLV limit. So for a shorter wavelengths, something like a 10 millijoule. For a longer wavelength, 1000 millijoule. But in 180, no, zero. There is big. Really, it is hazardous. So you should not all expose to this region at all. So only two wavelengths are allowed, and each one of them are really differing in their threshold limit values. So this is very important parameter. You should whenever you handle hazardous materials, you should also understand the harmfulness of these material. Here we are handling the light sources, UV light sources, so you have to be careful about the UV light sources and exposure to your body and the eye. Now these light sources can also be classified as the CW and pulsed light sources. CW is the one continuously glowing, like a mercury lamp, xenon lamp, and LED sources. And you can also make the frequency based light source like a pulsing light source, so on and off at a particular frequency. You can have on and off cycle, that is called as a pulsed light source. You can make a xenon lamp, can be a pulsed light source. It can have a pulse width of microseconds and milliseconds. They can have the frequency of hertz to kilohertz. Yes, is the one time per second is called as 1 hertz. One cycle per second is generally 1 hertz. If you have a 10 cycle per second, it's called as 10 hertz. If you have 100 cycle, it is called as a 100 hertz. If you have 1000 cycle, it's called as a 1 kilohertz. So you can also have LEDs pulsing. So LEDs can be nanoseconds and picosecond pulse width. They can have the frequency of 20 to 40 megahertz frequency. And this is where you can see that the high repetition rate light sources can be used as an excitation sources for fluorescence lifetime measurement. So you will find that the xenon lamps pulsing sources are useful in optical pumping of lasers, and pulsing light sources as excitation sources for the lifetime measurements, and continuously glowing lights like a spectroscopy instrumentation and the photochemical instrumentation. So this is how you have a variety of light sources, a CW pulse covering the different spectral region of ultraviolet visible. So they are all mercury light sources, xenon light sources, and LED light sources. So this is one of the LED that you can use it for a pulsed light source for the lifetime measurement. So if you want to have a different wavelengths, you have to buy a different LED. One LED cannot give all the wavelengths, as you see in the case of xenon lamp. So this is how the light sources are available in different formats and different wavelengths. You can see it. Different wavelengths are available, like all these LEDs, so you can really select them based on your requirement. You can have it at 360, or you can have it around 400, varied around 600, and so on. So variety of light sources are available, but each one of them costs a little higher, so you can have a selection of the wavelengths. Now you also have these pulsing LEDs available at different wavelengths and different time resolution. This is important. So depending upon the requirement, you can select your proper LEDs for proper your application that you are interested in. So this is how you can summarize the light sources. They are mercury light sources. You can put them as a low pressure, medium pressure, high pressure. You have xenon lamps. So xenon lamps of different powers, and xenon lamps can be a CW and the pulse light sources. So whenever we talk about light sources, you have to detect the light intensity also. For that you need a detector. So important component in all these instrumentation is light source and detectors. So you always look at the detectors based on their application, right? So what kind of detectors you want to use it. And whenever you procure or handle the detectors, so you should understand the important characteristics of the light sources, the detector that you are handling it. The first characteristics you will look for is the sensitivity. How sensitive is your detector? Is it low sensitive, high sensitive, what spectral region it is more sensitive, and so on. And the second point you always look at is the spectral response, spectral what wavelength your detectors can cover. They can cover ultraviolet region, blue region and the visible region, red region and the visible region, or in the NIR region, and so on. So the wavelength response is also important. These two are very prime important characteristics when you look for the detectors. The third one is the response time, how fast it responds. So that is going to be important parameter when you want to use it for time measurement application. Now, a signal to noise ratio is an important parameter which really decides how good is your spectrum will be, how good your parameter that you are being measured. So these are the 4 points. Out of these, I would mention sensitivity and wavelength as important, and these are also two, or other two, a responsive signal is also important. And the fifth one is the stability of the detector. How stable is your detector? How long you can use the detector to have the stable readout is also important. And based on the convenience, you have to really look at what kind of detector you are going to use it for your application. The cost also decides. If the cost is very high, you may not be able to have an access to the very high cost. So depending upon the application, the cost also changes. When you want to go for a pulse measurement, detectors are expensive, but normal measurements like a photodiode and PMT, they're all less expensive. So these are all the detectors characteristics that you should look for before start looking at the detectors that you are interested in. Now, how these photodetectors work? They all work based on your photoelectric effect, which was given by Albert Einstein. So one photon absorbed by this material, ejects one electron. That's called as the primary electron, and this electron is really used as a measurement of photocurrent. Now the electron, whatever the light that you give it, the excess energy that you are giving it is acting as a work function for the ejection of electron. This electron is really used to measure the current, and now photon to electron, electron to current, and you should have a converter, current to voltage, display the signal as a voltage proportional to the number of photons. So this is very important. This is how the phototube or general photodetectors or photodiode work. You have a light impinging on the surface of the material, electron ejection, and then you have a measurement of current, and then conversion of current into voltage and recording the signal. This is how it works. Now, important parameter is the sensitivity is coming from your quantum efficiency of your detector, as I already mentioned about the first point, sensitivity. The second is the spectral response. So depending upon the cathode material that you are using it, the spectral response will change. You can have a silicon photodiode covering the UV and visible region, and PMT based on a gallium arsenide phosphide is UV and visible. whereas your PMT little far away from the UV and the entire visible region if you are using a gallium arsenide. So the spectral response basically depends on the photocathode material that is being used in the detectors. So the quantum efficiency and spectral response are very important parameter. They all depend on what is the material of the photocathode that you are using, that is going to decide the quantum efficiency and the spectral response. So this is one parameter, that really one material that decides two properties. That is the important point to look at. Right, next level of the detector, photodiode that we said they are non-amplifying type of detectors. So whereas if you want to really amplify the signal, you need to have the better detector, which is basically a photomultiplier tube. We already mentioned about this photomultiplier tube when we discussed about the instrumentation on spectrophlorimeter. Now there are two basic class of the photomultiplier tube: side-on type and head-on type photomultiplier tube. Side-on type is generally used for any spectroscopy instrumentation, and head-on type is used for the photon counting measurement. So if you look at the inside, what is there? You have the window. That window's transmission is very important for the light that you are using it. And then you have photocathode surface, and it really ejects the electron focusing and acceleration of the electron. Further, you see the first dynode where it really gives the electron, and then the electron gets amplified by the further dynode assembly that you have. It last dynode collects the electrons and shows up the signal. That is the amplified signal. So this is how the PMT is functioning. And you have the next level of PMT is MCP-PMT, which can be used for time measurements. The time resolution, as we said, the time response is also important. Time resolution decides the application towards the time resolved measurements in fluorescence spectroscopy. MCP-PMT is being used for TCSPC fluorescence lifetime measurements. Now, if you look at the details of the principle of operation of the photomultiplier tube, first level is the photon enters through the input window. Second is the photons exciting the photons excite electrons, and from the photocathode, then the electron is really called as a photoelectron. These photoelectrons are focused with a focusing electrode on the first secondary electron emission surface, which is called as a dynode. The number of photoelectrons is multiplied via the secondary emission of electron, and the secondary emission is repeated several number of times on each of the dinodes in each of the device. Thus, the high gain is achieved by the photomultiplier tube. Secondary electrons from the last dynode is collected on the anode and is being measured as your signal, the current spike that is really used as a detection of the signal. And that is how the entire dynode assembly is amplifying the single electron that you get by the ejection of one photon. So this is the way the PMT works to collect the signal on the light exposure. Now, dynode shapes also decide many of these time resolutions. So there are 8 basic types of the dynode shapes: circular type dynode, box and grid type dynode, linear focus type, a Venetian blind type, a mesh type, microchannel plate type, and metal channel dynode type, electron bombardment type. So your microchannel plate, which is called as a MCP-PMT, so that is being used for the TCSPC application. So you will find that the different kind of basis dynode shapes will have different application. So you should also understand the MCP-PMT because which is being used in the TCSPC measurement. So you will see the series of channel. Each one of them will look like a dynode assembly. Inside the tube, what is happening is described here. In the channel wall, it reflects and finally gets amplified. So like this, every tube will get an amplified signal. That is the reason why MCP-PMT is much more sensitive than the normal PMT. The sensitivity is enhanced by the presence of the microchannel kind of a dynode structure, dynode as basis that you have it, that really amplifies the signal enormously. Now the windows that you have in the front of the photomultiplier tube decides the transmission characteristics. If you use a fused silica, it is transparent. It's called a spectroscopy, is a trademark, and then you will see that it starts almost from 150. So anything that is longer than 150 will get transmitted, otherwise UV and visible. If you use a UV glass, maybe up to 200 is fine. Beyond 200 it will transmit. Up to 200 it will cut off. And if you are using a borosilicate, maybe the entire UV is cut, you can have only visible. If you have a lime silicate, only from 300, rather long wavelength. So the transmission percentage, you can see it all varies depending upon the material, and the wavelength of the transmission is also dependent. Generally, they use something like a 3 millimeter thickness of the window glass, they use it. So the other parameter is the photocathode material. They also decide the spectral sensitivity as well as the quantum efficiency. We already mentioned about cathode materials decide. So different kind of a cathode material like a cesium iodide, cesium telluride, and bialkali, multi-alkali, and InGaAs, and all these type of the photocathode material, you can use it. So you can have the IR region. InGaAs is really for IR region. So that's the way they select your detectors and detector cathode materials, which can have a different kind of a spectral response. And the time characteristics is decided by your dynode type that you have it. There is a linear focal. We already mentioned about MCP type, and each one of them have got the different time, like a rise time, fall time, pulse width, electron transit time. They are all decided by your dynode type. Dynode type basically decides the what kind of a time resolution you can get out of the photo detectors that you are using, in particular photomultiplier tube. Now you can talk about full width of maximum, full width FWTM, it's called transit time measurements. Is basically transit time decides time spread. Actually, it's called the TTS, transit time spread, that you have it for the detectors. Now, another important aspect is the signal to noise ratio. You can see that the signal and the noise, around the signal you have a lot of noise coming up. So you can have a dark noise, or called as a background noise. So you have to really subtract all this noise, and you should have a very good signal. Now, for the sake of calculation of signal to noise ratio, you need to know about the mean value of the noise component, which is represented as a capital ID. And AC component of the noise is small id RMS value, and mean value of the signal is called as the IP plus D, and your IC component of noise is small ip plus D. So if you really want to look at the signal to noise ratio, it's the ratio of the capital IP divided by small ip plus D, and that is what is called a signal. If you have the dark ID, dark ID is very low, then you can really look at the signal to noise ratio as a capital IP divided by small ip, and that is how you can look at the estimation of a signal to noise ratio based on these parameters that you have from the instrument PMTs. Now, one of the leading manufacturers worldwide is the Hamamatsu. Hamamatsu makes a different kind of a photomultiplier tube. Hamamatsu R92 is a wide spectral region coverage PMT. So you have a blue PMT, red PMT, and large wide range PMT, and so on. So depending upon your requirement, generally fluorimeters, they use a broad spectral range like R9 to 8 family of the photomultiplier tubes. So this is how you have a different types of the photomultiplier tubes and characteristics of the photomultiplier tubes. You have it. They can be used for different application. The next detector that you have to look at is the photodiode. The photodiode looks like this is the real geometry, real appearance of your photodiode, and you have two pins, and then the electronic symbolic presentation is a photodiode with the absorption of the light. LED is emission of light. This is how the symbolically they are different, And these photodiodes come in a different format. This is for you to feel the formats available for the photodiodes that you have commercially available in the market. And you should understand, because some of them are very important when you handle the fluorescence machines or a photochemical instrumentation. Now look at the details of the diodes. So you see the general PN junction, PN diodes is basically a diode, and in between the PN junction, if you really put an intrinsic semiconductor, it's called as a pin diode. And avalanche photodiode is also the same pin diode, maybe it's more sensitive, and it is also applied for high frequency areas. And now you look at this different configuration, different arrangement, pictorial presentation of the PN junction, and PN junction with the I intrinsic layer. Normally intrinsic layer is undoped. P is a p doped, N is n doped, and intrinsic is undoped. This is how you can see that the pin diodes are being produced. So they find a lot of application towards the photosensitive photo detection. Now in the pin diode, when the light falls on it, and you have the holes and the electron separation, and they really flow in the PN junction, so you can really see that the high level of injection of electric field really makes to apply for a high sensitive applications, and also it is used for the uh, high frequency application. And now if you go for a APD, APD really finds a real high frequency application. And APD again is a pin diode, but operates in a reverse bias. That is the fundamental difference between a APD and a pin diode. And forward bias, it is working for a normal pin diode. Reverse bias is being used for the APDs, and they in fact almost better than sometime PMTs in terms of high frequency application. You get a good amplification, because you see an avalanche effect in your photodiode that is happening it when the light is falling on the photocathode surface. Now APD, you should understand some of the important factors. So it has an active area somewhere like a 1 millimeter square, and really it is difficult to focus on the APD because 1 millimeter is very small, so the sensitivity is too low for most measurements. Now you have a dead time somewhere around 100 nanoseconds, so you can see the frequency of around 110 megahertz. Routinely, this type of APDs, they use it for TCS, PC, and FCS application. And APDs have high quantum efficiency at real wavelengths, and detectors for different choice of the applications like a TCS, PC, and FCS, and so on. So this is how you will find the pin diode and avalanche photodiode, find application in the light detection. You can use a normal diode also, photodiodes. So you can have a diodes as a set of different region of wavelengths is possible. Silicon photodiodes, gallium arsenide photodiode, germanium, in-gas photodiode. So like this, photocathode materials really decide, as we mentioned about this photocathode materials on the photomultiplier tube. Here also the materials that they use it, they really have this junction materials. They really decide the sensitivity, spectral sensitivity of the photodetectors. These photodiodes can also be used as an array detector. So you can have organize them as an array, which finds a lot of application in the spectral measurements. As a one stroke, there is no movement of grating is required. So you disperse the light with a grating and with array elements. So that is really facilitates the faster measurement of the spectrum that you are looking at. For example, if you are looking at an absorption spectrum or an emission spectrum, you don't have to scan it. In 100 milliseconds, you can get the entire spectrum that you are recording it. So you will always see that something like 1,024 elements of diodes arranged as an array, linear array, single line linear array, which really facilitates the measurement of the entire spectral distribution of the light intensity. This is very, very important for the spectral measurements in a faster mode. So you can also compare PMT and PDA. PMT requires, if you look at the top picture, which really talks about the PMT based detector, and you need to move your grating to get the spectral measurement. PMT is for a single point measurement, whereas your diode array is a multi-wavelength measurement. So you can see every point is measured at every wavelength. So you are trying to make a plot of the spectrum absorbance versus wavelength in the case of spectrophotometer, in the case of fluorimeter, intensity versus the wavelength. So you can see that you have to move the grating, whereas here in the array detector there is no movement of grating, it's faster. You get the entire spectrum recorded in 100 milliseconds. This is an advantage of PDA, but PDA has its own disadvantages also. The spectral resolution of the PDA may not be as good as your grating and the PMT based detection system, and PMTs are more sensitive than PDA. That is also you should understand. If you want to have more sensitivity, PMT is a good choice. Lower sensitivity and fine and lower spectral resolution, okay, PDA is fine. But if you want to have a good spectral resolution, something like a 0.2 nanometer spectral resolution, good to have in PMT. Whereas PDA will have a resolution of the order of 2 nanometer. You may not be able to get a very high resolution in a PDA based machines. Now, PDA, the major advantage is the faster acquisition. If you want to really record the faster absorption spectrum, faster emission spectrum, it is possible to use the PDA, even if you don't mind about the spectral resolution. So that's where you will find a lot of application for PDA. And equivalent to this PDA, but they're much more sensitive, or otherwise CCDs are alternative detectors. CCDs are low light detectors, whereas PDAs are high intensity detectors. PMTs are much more intensity sensitive to the PMT. You know, if you look at the sensitivity order, PMT is the highest sensitivity, and then CCDs, and next is the PDA. But CCDs will get saturated if you put more light on the detectors. Right? This is the a comparison between PDA and CCD. You can make it. CCD you can use it for low light application. PDA you can use it for a high intensity application. That's the way you should classify. The purpose CCD also gives the entire spectrum in one measurement, like array detector, that photodiode array detector that you are looking at it. But what is the fundamentals of the operation of the CCD? If you look at it, the CCDs were invented in the year of 1970 by Bell Labs. It is a silicon chip is structured as an array of photosensitive pixels, and you can use it. Then you have an advantage of CCDs. Instead of making as a one linear array, you can also have the matrix XY matrix, and then you can work like a camera. That is what you are using as a camera in your most of the mobile phones and the TV cameras and cameras in any purpose that you are using it. They're all based on a CCD, which will have an XY array of the elements. So the number of elements that you have is defined as your resolution. This is what is called as a pixel resolutions. You call them as a megapixels, right? Gigapixels, and so on. So a number of megapixels are more, your resolution of the camera is more. So for a spectral measurements, you don't need too many. So maybe you have 1024 elements, or maybe 4000 elements you can have it. So when you have 4000 elements, spectral resolution is better. If you have 1000 elements, the spectral resolution is lower. That is how you will see the spectral resolution is connected with the how many pixels you have it in array, a linear array, or in a XY matrix. So CCD is also finding an application not only in spectral measurements and also in the area of imaging, luminescence imaging, photo imaging, biological imaging, and so on. Now, again, what is happening in each of the pixel, like what you have seen in photodiode, light falls on each of the pixel, and then you have the ejection of electron and get digitized analog to digital conversion. Then you measure the signal. So that is how your CCDs are working. CCDs are really becoming compact, and they are versatile. It can do XY measurements. You can also really make a 3D plots like a you can really see what we have seen in the measurements, excitation, emission. So CCDs can also give you a 3D plots. That is possible. Now you can also have the multi-channel detection possibility in the case of CCDs. So that really helps you to at a time you can measure different channels. That is an advantage, but it's very expensive detector. But it is possible. In principle, it is possible. You can have a dual channel like a double beam spectrophotometers or a multi-channel. That is possible. Now the next level of CCD is called as the intensified CCD. It's a front and back illuminated sensors. They are more sensitive than CCDs, so you can really look at it. Very low light application, you can still find it. Efficiency of photon detection is much more. And then the CCDs, ICCDs can also be gated. This is for a time resolution measurements, and gating to the time resolution of the order of few picosecond it is possible. And you can see that the ICCDs can increase the spectral sensitivity, can really increase the time sensitivity, and then they can cover a region of ultraviolet to be visible and NIR. So these are the one of the few companies worldwide they make manufacturers. NR, this is being procured by Oxford, and they really look at the manufacturing of the ICCDs. So here we have seen the detectors starting from your photodiode, photomultiplier tubes, and how exactly photomultiplier tubes are advantageous over the photodiodes. Photodiodes are less sensitive when compared to the PMTs. Otherwise, the PMTs are more sensitive, and then you can use it for a different application, and you can use a PDA also for a spectral measurement, CCD spectral measurement. So PDA is less sensitive when compared to CCD. CCD sensitivity can further be enhanced by ICCD, and the time measurements can be really integrated into CCD by using a gating principle. So it's called the gated ICCD. So you have a variety of the detectors starting from your diodes to the CCDs and ICCDs. So to summarize what we have discussed today, we have discussed about the different light sources covering the Mercury and Xenon lamps, details of all these light sources, application of all these light sources, detectors starting from diodes to the PMT, and to CCDs, PDAs, and ICCDs. So this really gives you a lot of information about the nature of the light sources being used in the spectroscopy measurements like absorption spectroscopy, fluorescence spectroscopy, and time resolved fluorescence and photochemical instrumentation. Detectors also we have taken care so that it can be used in photophysical and photochemical experimentation. Right, with that, I end the session on the light sources and detectors. We will see in the future upcoming videos about the different components of the fluorimeters. Thank you.